Hi everybody, in this video we are going to talk about resonance structures. Let's first review what resonance structures are. Resonance structures are just a set of Lewis structures that all contribute to the structure of a chemical. Now before we go on, let's talk about two types of bonds. They are the sigma bond and the pi bond. Sigma looks like that and pi looks like that. So in a single bond, there is one sigma bond. In a double bond, there is one sigma bond and one pi bond. So the red bond is the sigma bond, and you could think of the green bond as the pi bond. Now for a triple bond, there's one sigma bond, which is the red one, and there are two pi bonds, which are the two green lines. So now that you know what pi bonds and sigma bonds are for now, we'll go into it in further detail in the future. Let's move on to more things about resonance structures. So by combining all the Lewis structures, you get something called a resonance hybrid. So as an example, I drew out the three resonance structures for carbonate, and I combined them by putting everything in brackets, of course, and putting this triple bar. And this triple bar is like an equal sign, but it's more like an equivalence sign. It's like an equal sign, but instead of for numbers, it's for structures. So when you combine these three structures together, you get what is called the resonance hybrid, which is the one over here. And notice how there are dotted lines and there are solid lines. So when you see a solid or bold line, these are where the localized electrons or bonds are. In other words, they don't move and they stay constant throughout these structures. For example, this bond over here, which is a sigma bond, stays constant throughout the three resonance structures. As you can see, there's a sigma bond here, a sigma bond here, and a sigma bond here. So that's why the sigma bond here is kind of like a constant. It doesn't move. Now, on the other hand, you have what is called delocalized electrons or bonds. Now, this time they move, and these are written as dotted lines. So, for example, this second bond over here, or I could circle this one, it doesn't really matter. This could be the bond that moves, and notice how this pi bond over here does not stay constant, and notice how once you go to the second structure it disappears. So for this reason, the pi bond, which is this one over here, or you could think of it as the green one as circled over there, is something that's not constant. So therefore this pi bond can be considered a delocalized bond because it hops around from this oxygen to this oxygen and then to this oxygen. So that's how you draw the resonance hybrids, by drawing the bold and dotted lines and making sure that you distinguish between the two. Now, what's with the negative 2/3? Well, the thing is that you could think of this in two ways. The first way you could think about it is that the carbonate has a -2 charge, if you remember, and this -2 charge is distributed evenly among the three oxygens, and therefore each oxygen shares the -2 charge equally, so they split it among three, and that's why it's negative 2/3. Or you could think about it this way. You see that this oxygen, or let's look at this oxygen over here. This oxygen over here has a -1 charge 2/3 of the time. The third time it has it, but the second time it doesn't have the negative charge. So for every 3 times, it has a -1 charge 2 times. So -1 times 2/3 of the time is going to be -2/3 on average. Now that's a harder way of thinking about it, but it works in the end. Now another way to indicate that an atom is partially charged, which means it's not like -1 or -2, instead it's like a fraction. You could also use a symbol known as lowercase delta, and I don't know really how to draw it, but it kind of looks like this. I don't know, it looks like a G, but like without like that part over there. So for this oxygen atom, you could write this negative, because this is saying that the oxygen is partially negative. That's what the lowercase delta stands for. It stands for partially, and in this case, when you put partially negative, as seen here, then you're saying that this oxygen atom is not -1, but it's like a fraction of -1. And that's how you indicate something called a partial charge, which is not a full charge, but like a fraction of a charge, such as 1/2 of 1. So we'll get more into that later, but let's now look at how exactly we draw resonance structures. So the first way, of course, is to move the pi bond around. In the last video, I just told you to move the double bond here and here, and that's just moving the double bond around, or just moving this pi bond, or the second half of the double bond, around here and around here. But I forgot to mention this in the last video. Whenever you move the double bond around, you have to make sure that the number of electrons corresponding to that bond makes sense. So when I move the double bond from here to here, I can't keep the 6 unbonded electrons there. I have to change it to 4. And in the same sense, when I move the double bond from the top to there, I have to make sure that the electrons here add up to 6 and not 4, because remember, oxygen needs an octet, so it needs, 8 valence electrons, and that's why when you shift it from a double bond to a single bond, you have to make sure that the number of non-bonding electrons adds up to 6 on that oxygen, since it's a single bond. So by moving the double bond around, it's a good idea, but it's pretty risky, to be honest, because you can get confused, and sometimes it doesn't even work for all cases. Now, there's a safer way to think about this method. Instead of thinking about it as moving a double bond around, think of it as just rotating the molecule around. So, for example, this molecule rotates to become that, and that molecule rotates to become that. So think of it as a rotation. So it rotates twice to get the 2 other resonance structures, and that is another way to get resonance structures, by rotating the Lewis structure and basically just creating all the possible structures given the rotations. So that's a safer way of thinking about it, but again, it does not work in all cases, and honestly, that's not really what resonance structures are meant to be. Instead, in this video, I am going to teach you the legit way of doing resonance structures, a way that uses the idea of resonance structures and how they work, instead of just a neat little trick that works in some cases but not other cases. So over here, I will introduce to you this idea. So resonance structures can be formed from one Lewis structure by moving electrons around. So let's read the very first step. Your number 1 goal is to make sure that you are not making any expanded octets for any atom unless they are in period 3 or higher. So, for example, in this example, we moved the double bond from here to here, but by moving it, you have to make sure that there are enough electrons to make an octet, but not too many electrons. So you always have to keep an eye out for that. And remember, just rotate the molecule, and that's a safe way to do the method that I just mentioned. But of course, in this video, I plan to teach you the legit method of doing resonance structures, so you might not even have to do the rotation technique anymore. So let's read on. It is sometimes okay to have deficient octets, but your goal is to always have an octet if you can. That is the number 1 contributor to stability. Now, the number 2 thing that determines stability is formal charge. So we talked about this in the previous video. The lower the formal charge, the better. Now, step 2 states that you can change lone pairs into pi bonds, and you can change pi bonds into lone pairs. Or in other words, you're just changing the location of the electrons or moving them. Step 3, you can move a pi bond onto another bond that shares 1 or more atoms with the pi bond. I'll show you how this looks like, and it's nothing like what we did here where we shifted the double bond around. That's just no. So I'll teach you how to do it with the examples that we will do in the future, but let's go on to step 4. This is rare, but you can also move single electrons using half or hooked arrows. You can split a bond into one electron on each atom with half arrows. So let's see how that looks like. You can split a bond into one electron on each atom. So I'll write 2 atoms there. So I have to split them onto one electron on each atom with half arrows. So it'll look like that. And in the end, you'll get 2 atoms that are split apart, but they have 1 electron on each of them. Or you can combine 1 electron from each atom to form a bond with half arrows. So like this probably. And then you get the bond back again. We can use this rule for molecules with an odd number of electrons or for radicals, which are chemicals with unpaired electrons. Now, the last step is probably the most important. The last step states that you cannot move atoms. So, if you start moving atoms, you're creating isomers and not resonance structures. Isomers are things that have the same chemical formula but have a different structure. So, in these 2 structures, you can see that they are clearly different. One is a branch structure where it branches out, and the other one is a linear structure where it just goes in one direction. Now, both of these have the same chemical formula, but they have a different structure, and these are known as isomers. So, we're getting a little off topic, but that's just the difference between isomers and resonance structures. So remember, in resonance structures, only electrons move. The atoms do not move. So, just remember that, and you will be fine. And also, one more thing, when you have an arrow that's like fully developed, that indicates that 2 electrons are moving, and a hook or a half arrow will indicate that 1 electron is moving. So those are 2 keynotes, and now let's do some questions. Acetate, which is a polyatomic ion that you memorized, hopefully. And let's try drawing this. So this is actually a condensed structural formula, which means that the atoms are not clumped together. Instead, they are spread out to show you the distribution of the atoms. In other words, they tell you the order in which the atoms go. So first, let's draw the C. And this time, I'm not going to count the electrons because I'm going to do it in terms of bonding. Or to be more specific, I'm going to talk about how many bonds an atom needs to fill its octet. So when I talk about bonds, I'm talking about pi bonds and sigma bonds. So a single bond has 1 bond, a double bond has 2 bonds, which are 1 pi bond and 1 sigma bond, and a triple bond has 3 bonds because it has, well, 1 sigma bond and 2 pi bonds. So when I say a bond, I'm referring to either a pi bond or a sigma bond. So carbon needs 4 electrons or 4 bonds, either the sigma bond or the pi bond, in order to have an octet. So since this is a condensed structural formula, I am going to follow the order in which the atoms are given and draw them accordingly. So this carbon will have 3 hydrogens attached to it. So each hydrogen needs 1 bond, since it needs a total of 2 valence electrons to be satisfied. And this carbon needs 4, so it'll connect its last one with another carbon. And next to carbon is an oxygen, and oxygen needs 2 bonds to work, so oxygen will need 2 bonds. And don't forget the lone pairs that are on the oxygen, because the oxygen, of course, needs an octet. And now, what do we do for the last one? Well, notice how there's a -1 charge on the acetate anion, and also notice that all the atoms so far, except for the one that we haven't finished using, have formal charges of 0, and you could do that by calculating it on your own. So they all have a formal charge of 0, and this tells me something. This tells me that either this carbon or that last oxygen is going to have a formal charge of -1. And since we usually don't see carbon with a -1 charge, since oxygen is more electronegative, I think oxygen is going to be the one with a -1 charge. Now, what does that mean when I say that oxygen has a -1 formal charge? Well, I mean that it has an extra electron. And if it has an extra electron, that means it has 7 valence electrons, which means that it needs 1 more electron to be an octet, and that's why it needs only one bond. So notice how this needs one bond and this needs one bond, so they're perfect for each other, and thus the last oxygen will be attached to the carbon with one bond because it needs only 8 electrons and it already has 7. So this will have the -1 formal charge. So let me erase all the stuff around it, and now let's begin doing resonance structures. So resonance structures, the rules tell us that you can change a lone pair into a pi bond, and you can do the opposite. So let's do that, and let's see if we can obtain a reasonable Lewis structure. So before we do that, let's talk about the very first method that I mentioned in the previous video and the method that I mentioned in this video, where you simply just move the double bond. And let me show you how that looks like. So let me tell you something ahead of time. I'll tell you that the method of moving the double bond around works, especially for this case, because they're both essentially oxygens and they're attached to a central atom. So it will work. So it will look like this. So let me finish drawing this. And this time this oxygen will have a -1 charge. But notice that when I do that, I have to not only move the double bond there, but I also have to change the number of electrons so that it makes an octet. So for this one, instead of having 6 non-bonding electrons like it does here, it has 4 over here since it's attached to a double bond. So the risk in using this technique is that when you're switching bonds around, you have to also change the number of electrons on the atoms in terms of the non-bonding electrons. So it's a risky move, but it works. But I'm here to show you the legit way. So let's do the legit way. So the legit way says that we have to move the electrons around. So we can move lone pairs into bonds or vice versa. So here's what I'm going to do. I'm going to move this pi bond over here and change it into a lone pair. And notice how when I remove that pi bond, this carbon has only 3 bonds, but it needs 4. So how do you make it 4 again? Well, remember there's another oxygen, and that oxygen can actually donate electrons. And you could think of it this way, since it has a negative charge, it wants to donate electrons and get rid of them. So you could think of it that way, and think of the oxygen as donating its electrons since it has too many electrons because it has a negative formal charge. So it donates the lone pair and changes it into a pi bond, and now the carbon has 4 bonds once again, and it has an octet. So when you draw the resonance structure, it might look like this. So it has 3 H's, that stays the same, and the carbon now is attached to an oxygen with a double bond on the top right, and on the bottom right, it is a single bond with a minus charge as its formal charge. So notice that all we did was move electrons around to produce the resonance structures. So this is the legit way of doing it, but we're not finished. We have to draw the resonance hybrid. So let's get going. So the resonance hybrid, let's keep the things that stay constant with bold lines like these ones over here, and let's continue that. And notice how the sigma bond here, 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 and here stays constant. So because it stays constant, we can draw those as bold lines. So it might look like that, but notice how the double bond, or to be more specific, the pi bond over here, alternates from the top to the bottom, and it's not permanent because from here to here it disappears at the bottom. So because of that, we have to draw a dotted line here, and notice how this double bond appears, but it wasn't here to begin with. So because it wasn't permanent, it also deserves a dotted line. So this is the resonance hybrid for acetate, and since these two oxygens are sharing a -1 charge, each of them has a charge of -1/2 and -1/2. And you could also write the -1/2 as a delta negative and a delta negative, but I decided to do it in terms of numbers since it's more specific that way. And yeah, this is the resonance hybrid for acetate. And let's take a look at a few notes. So at the beginning, I wrote it, but I didn't say it. So the circles around charges are optional. So you don't have to actually put a circle around the minus. That's just based on what you want to do. So it's optional. The second thing is that you don't have to draw unbonded electrons in resonance hybrids. So in your resonance structures, you have to draw the lone pairs or the unbonded electrons, but in the resonance hybrid, you don't have to do that. So now let's go back, and now that we've done acetate, let's do the next question, benzene. So benzene is a very special molecule that's super stable, and you'll see why it's stable. So let's draw the resonance structures for benzene. So we have to move electrons around. So how about this? Let's take a look at rule 3 and apply that. You can move a pi bond onto another bond that shares one or more atoms with the pi bond. So it looks like this. If I move the pi bond here, then don't you think that this carbon will have too few bonds? And don't you think that this carbon will have too many bonds? Because if you move it here, the carbon here will have 5 bonds, and that's too much. So what do we do to relieve the stress on this carbon? Well, we can move this double bond here. But once you move it there, this one's happy, but this one is stressed because it has too many bonds now. So how do we fix that? Well, we can move it here. And notice that once you move it there, you might assume at first that this is really stressed, but you have to remember that this is a single bond because it was moved. And in the end, you get this. So these two are your resonance structures for benzene. So notice how I moved the electrons multiple times until all the atoms were happy. So let me draw the resonance hybrid. So it might look like this. So I'm going to have carbon, 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 and carbon. And I'm going to have 6 hydrogens attached because that's a constant throughout the entire process. And the single bonds are constant between the carbons, so I'm going to draw those as bolded lines. But one thing does not stay constant. The double bond here disappears in the next structure, so therefore it is delocalized. So I have to draw it as a dotted structure, and this applies to all the double bonds, or to be more specific, all the pi bonds. So I'm going to draw dotted lines for all the pi bonds since they're all not permanent, and in the end you get this as your resonance hybrid. And it's a little bit messy, but I'm sure you understand it. So let's move on to the next question. Thiocyanate, SCN-. This is another polyatomic ion, and let's just draw it. So carbon needs 4 bonds, sulfur needs 2 bonds, so I'll do it for sulfur first. And the last 2 bonds for carbon will go to the nitrogen. Now, since there's a minus charge there, this nitrogen will have not 5 valence electrons initially, but 6 valence electrons. And if you have 6 valence electrons, you need 2 more bonds, and therefore it's a perfect fit. And this will have a -1 formal charge. So now we need to draw the resonance structures. So remember what I said about acetate, how if something has a negative charge, it tends to want to donate electrons. So in this case, nitrogen is nice enough to share its lone pair, so it's going to do that for that. But now the carbon has 5 bonds and it needs 4, so it needs to get rid of 1. So what if this pi bond here just went there as a lone pair? And in the end, you get something that looks like this. So triple bond there with, I think, that there, and boom. And let's put the -1 formal charge on the sulfur, since it has a -1 formal charge once you do the calculations. So let's read this note I wrote. Not all resonance structures, like Lewis structures, are created equally. Some are more stable than others. So which resonance structure is more stable? Well, the first one, because the minus charge is on the one that wants the electrons, or the one that is more electronegative. And since nitrogen is more electronegative than sulfur, then nitrogen will want to hog the electrons more. So it's more reasonable that the negative charge, or the extra electron, is on the nitrogen rather than on the sulfur. So everything makes sense here. So this is the more stable Lewis structure of the two. Now, before I move on, I want to talk about something that I forgot to mention. It has to do with the resonance hybrids. So, the resonance hybrid is the most accurate depiction of the actual structure of carbonate. So, all three bonds are identical according to the resonance hybrid, but in the Lewis structures, you can clearly see that these two bonds are different from that one. But when you go into the lab and you measure it, in reality, all three bonds are identical, and that matches the structure for the resonance hybrid. So therefore, the resonance hybrid is the most accurate depiction of the actual structure of the carbonate anion. And in addition, all three resonance structures equally contribute to the hybrid, since they are all equally stable, and they are all equally stable because they are essentially just rotated copies of each other. So that's something important that I wanted to talk about, and now let's get back to the question. Let's draw the resonance hybrid for thiocyanate. So let's draw the S, the C, and the N. So which ones are localized electrons and which ones are delocalized? Well, the localized ones are the permanent ones. So I think for here, the double bond here is kind of permanent because in both of them there's a double bond. So I think there's a double bond here, and it's going to be permanent or localized. Now, delocalized, well, that includes this pi bond here, so delocalized. And this pi bond here is also delocalized since it doesn't occur in this picture, so delocalized. And the charges, or the -1 charge, is going to be distributed between the sulfur and the nitrogen. So it's going to be that and that. And I'm not going to put numbers since these two structures do not weigh in equally to the hybrid structure, since one structure, namely this structure, is more stable than this structure. And because of that, this contributes more to the resonance hybrid that we see in real life over this structure. So I can't say that the -1 charge is going to split evenly into -1/2 and -1/2 for the sulfur and the nitrogen, because this structure is more stable. So I would expect that the -1 charge would like to be here more than it is here. So maybe the partial charge in here is -3/4. Who knows? But this is the resonance hybrid for thiocyanate, and let's move on. So for nitrogen monoxide, I think I'm going to count electrons since this is a bit dangerous because it's not a typical substance, since this substance has an odd number of electrons. So 5 plus 6 is 11. So I'll keep track of my electrons here since it's a little bit riskier to do it by bonding, since there are unpredictable things that happen with odd number of electrons. So let's get to it. N and O, and I know that O wants to fill its octet first, so let's fill the octet for O. And I think let's make a double bond in order to make sure that the nitrogen gets as many electrons as it can. So this will have its octet, but let's see how many electrons we have left. So we have 4, 8 minus 8, that's 3 left. So this is the Lewis structure for nitrogen monoxide. But notice how we can also draw resonance structures. So let's try doing that. But since there are odd number of electrons, there's actually an unpaired electron, and this is where we could start using the hooks that we really wanted to use at the beginning. So let's try using the hooks. So if I get that one electron there and that one electron there, then you're going to form a triple bond. And if you form a triple bond, this oxygen will have too many electrons, so we have to relieve it. So we can relieve this by making one pi bond go to the nitrogen, since remember, at the beginning, the nitrogen was the one with the deficient octet. So by giving the pi bond to it, it now has a full octet. So now it might look like this. So this will still stay as a double bond, and now the oxygen will actually have 7 valence electrons. So let's label our formal charges. So this nitrogen here will have, well, it has 5 electrons initially, minus 3 non-bonding electrons, minus 2 bonds, 1 sigma and 1 pi, and you get a formal charge of 0. So this has a formal charge of 0, and this has a formal charge of 0. And how did I know that oxygen had a formal charge of 0? Well, remember, the sum of the formal charges adds up to the charge of the compound. Since the compound is neutral, if this is 0, then this must be 0, because 0 plus 0 is 0, which is neutral. Now, for this atom, well, we can look at the formal charges for this, and let's just go for it. So, let me think about this. Nitrogen has 5 naturally, but it has 4 non-bonding and 2 bonds, therefore nitrogen is minus 1, and as a consequence, O will be plus 1. Now you might want to try out another resonance structure. For example, you might want to move this lone pair and turn it into a pi bond, but if you do that, notice how the oxygen will have too many electrons. It'll actually have 9 valence electrons and not 8, and that's not good. So, for this reason, you cannot make any more resonance structures. So, these are your 2 resonance structures, and which one do you think is the stabler of the 2? Well, the first one, because there are 2 reasons actually. The first reason is because the oxygen is the one with the octet, and remember, the more electronegative atom should be the one with the octet. So it makes sense that the oxygen will have the octet and not the nitrogen. Now the second reason is because this structure over here has too many formal charges that are not 0. Meanwhile, everything here is 0, and if you're closer to 0 for your formal charges, it's much better. So, for 2 reasons, the first resonance structure will be the stabler of the 2. So now let's draw the resonance hybrid. Well, the resonance hybrid will just look like this. Oh, that's not an N, that's actually an O. Sorry about that. And we will have a partially positive end and a partially negative end. And the reason for this is because if you think about it, the nitrogen has a minus 1 charge in one of the 2 Lewis structures. So you could think of it as, well, half the time the nitrogen has a minus 1 formal charge. So that's why it has a partially negative charge at the end. But if you remember, this is the more stabler of the 2. So nitrogen will tend to want to be as neutral as possible. But because of this Lewis structure, although minor, it still contributes to the actual structure. Because remember, the actual structure consists of all the Lewis structures, or I mean the resonance structures combined. So this will have a partially negative charge, and this will have a partially positive charge. So now let's move on to the next chemical, dinitrogen monoxide. So let's figure out how to draw this. So I think that the nitrogen is going to be in the middle, since nitrogen needs the most bonds out of the 2 atoms, and I think it's going to be attached to nitrogen and an oxygen with at least 1 bond. Now, let's think about this. I think this time I will count the electrons and do it the first way that I taught it. So 5, 10, and 16. So 16 valence electrons minus 4 that we used so far is 12. So the 12, let's think about this. I think I want to fill the octet for oxygen first. So how about this? Let's just do that. And by doing that, I just used up 6 electrons, so that'll leave 6 left. And where should the last 6 go? Well, our nitrogen in the middle is happy. Well, no, it's not happy yet. It needs 8 valence electrons, and maybe you could form a bond here, and that will remove 2, so you get 4 left. And the remaining 4 could, go here. And voila, we have the Lewis structure for dinitrogen monoxide. So notice how nitrogen typically wants 3 bonds, but I gave it 4 this time because, I did it the first way by looking at the valence electrons instead of looking at it in terms of bonding. Sometimes one method is better than the other. And in this instance, this method is clearly superior to the other. So I drew this Lewis structure and it makes sense. So let's find the formal charges. So this will have a formal charge of minus 1, this will have a formal charge of +1, and this will be neutral. So these are the formal charges. Can we draw resonance structures? Well, I think we can. So let's try move electrons around and see what happens. And let me just erase all these numbers because we don't really need those anymore, and it takes up space, so I'm going to erase them. Now let's draw the resonance structures. So, we still have the N, N, and O combination because we are not going to move the atoms, we are going to move just the electrons. So, how should we go about doing this? This is going to be a bit tricky. So, how should I move the electrons? Well, maybe I could do this. Things with a negative formal charge tend to want to donate electrons. So, this nitrogen might be charitable, and it might donate a lone pair and turn it into a pi bond. But by doing that, this nitrogen has too many bonds. It has 5, but it wants 4. So it'll remove one by just giving it to the oxygen, because oxygen won't gain or lose any by doing that. Meanwhile, the nitrogen will lose because it won't be connected to the bond anymore. So, in the end, you get something that looks like this. And let's draw the electrons carefully, and it'll look like that. So this nitrogen will still have a +1 charge, but this oxygen this time will have a -1 charge. So I think these are the two resonance structures for N2O. And how can we tell which one is more stable? Well, the negative charge should be on the more electronegative atom. So I think this one wins because oxygen is the more electronegative atom and it hogs more electrons. So structure 2 is more stable. Now let's draw the resonance hybrid. So the resonance hybrid will be the 3 atoms, and it looks like the single bonds are permanent. It looks like the double bond is permanent on the left, but it looks like this is not permanent, so that's delocalized, and this is not permanent, so it's delocalized once again. And notice how in both pictures, the nitrogen has a plus charge, and it doesn't change. So the nitrogen in the picture will have nearly an exact +1 charge. So I'm just going to put +1 because it stays constant in both of the pictures. Now, in real life, of course, there might be one obscure resonance structure that might not have a plus charge on the nitrogen, but since it might not be as stable as the two we've drawn, then it doesn't really matter and we kind of just ignore it. So this has a charge that's really close, or maybe even exactly +1. Now the negative is actually distributed between the nitrogen and oxygen, albeit not equally, since this is the more stable, this is the more stable one. So this one might be the more negative atom than this one, for example, in terms of formal charge. So this will have a G, well, it's not a G, it's a delta minus, and this will have a delta minus. And I don't write fractions because I'm not exactly sure how exactly the negative charge is distributed between the two atoms. So I want to put that to be safe, and this will be my resonance hybrid for N2O. Now, let's move on to the final structure, triiodide, which is an ion that you did not memorize because it was an anion that I thought was pretty obscure and you rarely see this. So let's draw triiodide. So I, and I. How's this going to work? Well, let me put the I in the middle. So let's count the number of electrons, since this could get a little bit tricky. So iodine has 7, so 7 times 3 is 21, plus 1, 22. Now we have to bond them up, and that's -4. That'll give us 18. And how do we do this? Well, remember, iodine is in period 3 or higher, so it can form an extended octet, which is why, it has 2 bonds when it's supposed to just have 1. So let's now use the remaining electrons to fill the octets. So I think the iodine would prefer to have 1 bond if possible, and it could make an extended octet if it wanted to, but not too much, because it might overwhelm the middle iodine. So let's just keep it at 1. So if it has 1 bond, then the iodine needs 6 electrons that are non-bonding to have an octet, and same goes for this one. And for this one, well, how many electrons do we have left? So we used up, I think, 12, so we have 6 left. So I think the remaining 6 should go on the iodine in the middle. So let's get right to that. So I'm going to draw the iodine in the middle, and I'm going to put 6 around it. And this is an extended octet because this iodine has 10 valence electrons after sharing electrons with the other 2. So I think this is the Lewis structure for triiodide. Now let's find the formal charges. So the formal charge on this is, well, 7 minus, I think, 6 non-bonding minus 1 bond, that's 0. And since this is 0, then this is going to be 0. And, you know, we don't write the zeros typically, so let's not write the 0. And if these 2 iodines are 0, then the middle must be minus 1, because the formal charges added up together should equal minus 1. And I could prove this. So if you look at this iodine, well, if you look at it, it has 7 naturally, minus 6 non-bonding, minus 2 bonds, and that makes -1. So there you go. This is the Lewis structure for triiodide. Now, are there any resonance structures? Well, technically, yes, you could move it down here, theoretically, and form an extended octet and make this iodine in the middle have even more electrons. But let's try doing that and see what happens. So if I actually do that, and I put the electrons where they're supposed to be, so it's going to be here, 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 and here, 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 here. So I put all the electrons where they're supposed to be. So now let's find the formal charges. So this will have a formal charge of +1, and this will have a formal charge of -2, and this one will be neutral. So notice how our formal charges are off the chart. A -2, like, that's going to be super unstable. So although this is a quote-unquote resonance structure, it isn't a major contributor to the actual structure of triiodide. In fact, it might not even exist because this iodine has too many electrons. Like, an expanded octet can only go so far, right? So this is not going to be very stable, and things that are not going to be very stable, we typically ignore, and we don't count them as resonance structures. So you can simply just erase the resonance structure we just wrote because it's not stable enough for us to consider, since it has a formal charge of -2, and that's, you know, not very stable. So let's redraw this triiodide as we did before, with only 1 minus charge in the middle for the formal charge, and I think this would be the only structure for triiodide. So therefore, triiodide has no resonance structures. And before I end this video, I want to mention one more thing. Resonance stabilizes structures, especially those with formal charges. So for example, for N2O, notice how the resonance structures help the structure spread this -1 charge over a large amount of atoms, and this actually stabilizes it since the electrons are more spread out and, you know, it's more stable. And we'll get more into why this is in the future if I make a video on it. And for this reason, something like benzene, C6H6, is a relatively stable compound since it has resonance, because these delocalized pi bonds are going all around the atom, or I mean the structure, in order to stabilize it. So, in summary, delocalized pi bonds and delocalized formal charges really help in stability. So that's all I wanted to say for this video. It was kind of long, but that's fine. Hopefully you learned how to do resonance structures, and if you want more practice, just go online and look for some practice. And that's all for this video, and have a nice day.